Welcome to this micro session where we will take a look at this exercise that is sent as an evaluated exercise here. So the problem says that a bar, and let me mark it here, a bar of steel, I can use this one, yeah. A bar of steel has the minimum properties of SE, which is the fatigue endurance, a yield strength of 430 megapascals, and an ultimate strength in tension of 551 megapascals. So then it says that the bar is subjected to steady torsional stress, interesting, of 103 megapascals, and an alternating bending stress of 172 megapascals. Alternating, perfect. So problem is already telling us some hints here. First, it tells us find the factor of safety guarding against a static failure. I wrote it here. And either, and this is very important, either the factor of safety guarding against fatigue failure or the expected life of the part. Which one is it? We don't know yet, yeah? So for fatigue analysis, it's asking us to use either the modified Goodman criterion or Gerber in this case. I have put a few figures here that are extracted from the lectures and that you're going to need to analyze this. But first, let's tackle what we can know from the problems here. So there is no any missing information here. Okay. So first, let's take a look at the endurance limit. This one here. So if we remember, the endurance limit as it is defined in the lectures is going to be something like this. And then I have the marine factors here, Ka, Kb, and then continue until Kf, and then the theoretical endurance limit. Now, so two ways of seeing this. Already they are giving us, for sure, the practical or the ready-to-use endurance limit. So I don't have to work with any marine factors because, they're giving us as it is. Now, if in the case that you say, yeah, but if this is the theoretical and I would need to use the marine factors, then also we said in the lectures, and you had a quiz asking precisely this, that if no information is given about any marine factors, you need to use the unity. You need to use one, and that's it. Meaning for any way you could look at this, this is the endurance limit you should use. And why is this important? Because, let me bring this marker here, this one here comes to this formula here and this formula here if I needed to use it. All right? Let's continue. So we have then the yield strength. I will talk about this a little bit later. And then we have the ultimate strength in tension, yeah, which is 551 megapascals. When I come to the modified Goodman and the modified Gerber, yeah, I have this, they're written a little bit differently. And I mentioned also in the lectures that you can find different ways of calling it. And as I use in different figures from different authors, then it's normally that you can use this, you can have these differences here, yeah. So we found another data that we need here. Now, on purpose, I'm putting the equation, I wrote down the equations here that are needed to be used in case we need to calculate the safety factor. I didn't bring the formulas to expected life according to modified Goodman and the Gerber, which are different. It's based on a different curves. But I'll explain that also later. So now we have two pieces of data. Let's continue reading. So the bar is subjected to steady torsional stress. Okay, let me just jump that for a minute. And alternating bending stress. Wow, so alternating bending stress. Yeah, because the other one is steady torsional stress. So now we have almost all of the ingredients if I wanted to use these equations. I'm just missing the mean stress that I need there, yeah? So, okay, but let's give a stop here because we have analyzed all of this. Part that is given, but let's jump to kind of part of the resolution of the problem. Yeah. So when we talk about variable load, I've brought a couple of images here. So we see that if I have a bar under only alternating bending stress, it's going to look something like this. Yeah. So the bar is going to be some sort of fully kind of going to one maximum, then goes to a minimum, where the zero line is going to be the mean of that stress, alternating stress. Yeah, but that's not the only stress we have there. Yeah, so meaning that this is going to be, if these were only subjected to a bending stress, alternating bending stress, so this would be it, but it's not. Yeah, so this part here is going to be the alternating stress. Yeah, sigma A. Well, it's given already, so you don't need to do anything. Yeah. But then the main challenge, actually, of this problem is going to be to calculate or decide what is or which is the mean stress to be input in this formula. Yeah. Now let's continue. Now, when we look at this figure here, you see that we had some sort of, let's say that you had a only alternating dependent stress, but suddenly you applied another stress that kind of shifted that curve up. Yeah. So the only thing that happened was that shifted that curve up, and then you would say, so the mean line of my original case was this one, but when I applied a different or another stress, it just shifted up. Yeah. So this starts giving me some ideas about what is the value of the mean stress. Yeah. And again, just to make sure so you don't go rushing into this, no. Taking directly the steady torsional stress is not the mean stress. Yeah. So it contributes to the mean stress, but it's not exactly that value of 103 megapascals is not the mean stress that you need to use. Yeah. It contributes to it, is the main part of it, but is not the one that you need to use. All right. So the main challenge of this problem is in calculating this mean stress. You say, okay, but we have other things to do. Yeah, okay, let's take a look at them. So then it says, hey, we're analyzing this second, because this is kind of the ones that is more scary for people, yeah? It says, okay, but it says that I need to calculate either the safety factor or expected life. So when we talk about fatigue, we know in our, let me try to draw this curve. So remember that we have this stress life curve, yeah, this SN diagram, which was something like this. It went down, and then it came down again, and then it went like this, yeah. And this part here was what we know as the endurance limit. And then here on the top, we remember that this part was the ultimate strength value. Yeah, ultimate strength value. Yeah. And we said that, hey, anything that comes, and let me bring another line here, something like this. Let me see if I can just move it like this. Perfect. So anything that comes to this side is going to have a finite life, which means that it's going to break at some point, and we're going to consider that, it has a limited life. But anything that comes over here is going to be an infinite life, which means that we don't care about things. We just let it run, and that's it. Yeah. So, but hey, they're not giving any more data for this. So how do I know if this specimen is going to last more than or less than that line there? Yeah. And remember, we gave an agreement value for that part there. Yeah. So, how can I do? Is data missing? No, data is not missing, because we also said, okay, you know what? Before starting everything, you need to see if your design is going to fall into the finite life or into the infinite life. Yeah. So that's why I brought here this Goodman diagram. And we said that, hey, if according to your values, material values and alternating stress and mean stress, your operational point falls in, for example, here in the green area, then it's a safe life. You don't need to calculate for infinite life or anything like that, for finite life. So you can use directly these equations here, this one here and this one here. Yeah. But now, if your operational point falls, for example, in here, in the orange area, then it's going to fail because of fatigue, and it means that you are going to need to estimate the number of cycles that piece or element is going to last. Yeah. So your task in this case is kind of to recreate this Goodman diagram and see how your case where your case is located in this diagram. How can you do that? Say, well, I don't know how to do it. Well, you just recreate this with the values you are given. So we have the vertical line, which is the alternating stress line. You have the horizontal line, which is the mean stress line. I'm going to write like this. Yeah. Then you have several values that are represented here. You have the endurance limit, yield strength, and ultimate strength. So what you do, you write them. I'm going to omit the units. All of them are in megapascals. So this is the endurance limit, which is 260 to 76. Then we have the yield strength, which is 413, and then we have the ultimate strength, which is this 5 551. Yeah, and the same thing repeats here. So you have 276, you have 413, and then you have 551. Yeah. So how do I draw these green areas and yellow areas and stuff? Well, let's follow the diagram. I know that if I bring my ruler here, I need to, let's limit, the lines corresponding to the ultimate strength. So let me put it like these lines here, and this is going to reach to the other one because it's this one here. Comes, if you look at the Goodman diagram, it's going to be this one here, yeah? And then you have another one for the yield strength, and that's going to come all the way up to here, yeah. Then I'm going to rotate this ruler to make it like this. It's going to be this one here, and it's going to be this one here. Then it says, I know that the green area comes from the endurance limit, straight line all the way up to the intersection of the both horizontal and vertical line corresponding to the ultimate strength. Yeah, sorry about that hiccup there. So let's make a line here, solid line, and then I'm just going to try to draw it. It's going to be something like this. Boom. And then this one also is going to be something like this, all the way up to here. Can I? Well, just forgive me. This, well, it's supposed to be here. Yeah. So meaning that if my operational point falls in here, the formulas I need to use are these one, the ones that I'm showing like here, because they are infinite life, yeah, safe life, they call it. So, okay, but what's my operational point? Well, I do know that the alternating stress is 172 megapascals. So if I bring my ruler again, definitely this is going to be less than this. So my line or working line, let me use another different color here, maybe this one. It's going to be like this. Ooh, I'm going to just write a horizontal line. Draw a horizontal line. And this corresponds to my alternating stress, which is 172. Yeah. So the time I have taken here is because I'm just explaining how to do this stuff. But you don't need to draw this either. So you can just look it up and use this Goodman diagram that you have here and overwrite things there. Yeah. Then, which means that if my stress is somewhere around here, my mean stress is somewhere around here. So for sure, I need to use this one. Yeah. So again, the real challenge is determining who is the mean stress. Yeah. Now let's go now to the first part of everything, where everything starts. Yeah. So here we have answered, for example, some of the values that we need in the formulas. Here we can answer if I need to do infinite life or finite life. Yeah. And you can now see the hint of what I'm telling you here, where if it's finite or infinite life. Here you can see it right away if it's going to be finite or not. So this is not something to worry about. So let me move this one here. I have taken more than I wanted to. Maybe this one here. Oh no, it's not letting me. Okay, doesn't want me to. But now, they're asking me to find static failure. When we talk about static failure, we saw that in the failure theories lecture. Yeah. So now, if they're giving me mark it with this one, a yield strength, yeah, still, so definitely this is a ductile material, which means that if I wanted to investigate the static failure of this, let me write it down here, I would need to use, at least of what we saw in the lectures, a couple of theories, either Tresca or von Mises. This should be uppercase. Yeah, I suggest you use von Mises. Yeah, right away. You could use both and do the same analysis with Tresca also, but von Mises is something that you're going to be using even more and more in the future. Yeah? So what von Mises says? Well, von Mises says, you know what? If you want to calculate this equation as per se equation, so you just need to use so we're talking about the plane, yeah? So you need to use this equation here, which is that how it was, so something like this. So it was like 1/2, I believe so, was one. Oh, sorry, this one here. minus this one here, yeah, 2 power 2, and then it had other components. I need to check it out, this formula, because sometimes I just, no, it's that one, yeah. And look at this, I'm taking just these two because they are kind of, we're talking about the plane. I just need to make sure that I'm writing the formula from memory and it is correct. Yeah, I have brought here the equation. Yeah, it is exactly like that. So just move these two to this side and then put it back here. Square root of it, and then it would make sense. Yeah. Then for Mises, we have it here. We have it. Okay. Perfect. This is an important equation actually. Yeah. Awesome. Now let's come back to our problem. Yeah. So we have this. You say, but what is torsional stress? Well, torsional stress, and let me write it here. Torsional stress is the stress caused by torsion. Does it make sense? And what type of stress is caused by torsion? Well, not torsional stress, but in the elemental stresses that we have seen, for example, if I have a bar like this, and this bar is subjected to a bending or alternating bending stress and a torsion here. So we know that bending stresses create normal stresses or action stresses, however you want to call it, normal stresses, yeah, here. And torsion creates shear stresses. So then, what is a torsional stress? It's a stress created by torsion, and that's a shear stress. As simple as that. Yeah. So if I take an infinitesimal cube of this bar here, so something very small here, yeah, and I put it, it's going to be a square. So it's going to be something like this because I'm in the plane. So I'm going to have then my normal stress created by bending, and I'm going to have my shear stress, put it in any direction you want. We don't know that yet, and we don't care. Yeah, the shear stress here. So then you can put it back here, so you can see this normal stress created by bending, and then for sure this is going to have something like this. And like this, just to follow the reciprocity of shear stresses. So this is something also we saw. So which means that what is the static failure safety factor? Well, you calculate, there are several ways of doing this. You calculate the principal stresses here, then you put it into von Mises, then you are going to get a sigma, and that sigma is going to be compared larger, smaller than the yield strength. And this comparison division basically is going to give you the safety factor. That's it. But now the unanswered question of the whole process here is, who is the mean stress? And as a final hint, what I'm going to tell you is that now that you have found this one using von Mises, search in the literature von Mises. One thing that happens in von Mises is that helps you combine normal and shear stresses. Normal and shear stresses are in different directions. That's why you cannot consider that the torsional stress given here, the steady torsional stress, is exactly the mean stress, because the alternating bending stress and the shear stress are in different directions. So you need a way to combine them. Yeah, and then you could say, well, von Mises in this case is the one that helps you combine things. Then you could, if you work out this formula here, together with the definition of what principal stresses are in the plane, which remember is this one here, plus minus this one here. Let me delete this so you don't need it. Square plus tau. You could get to a formula. It's very quick, and it's in the textbooks also. That says, hey, you know what? Equivalent stresses according to von Mises, when you don't use purely the definition of principal stresses, is something like this. Let me see if I remember the formula correctly. So it's something like this one here plus this one here. Yeah? This is going to give you exactly the same as this one here. But again, your main challenge actually in this task is finding out or deciding what is the mean stress, because the rest is given for you. I hope this extended explanation of the exercise helps you in completing this task. Again, just a summary. You don't need any marine factors because the endurance limit is given for you as it is. Second, please use von Mises. You can use Tresca also if you want to, no problem. I suggest von Mises because it's the most used, yeah. And also, well, use von Mises. You know how to do it to calculate what is the static, the stress factor against static failure. The safety factor against static failure. So it's just a small recap of what you did in failure theories in the lecture. Yeah. Then you need to think about what is the mean stress, because the mean stress is going to give you the answer for finite or infinite life, although I already told you the answer for that. And secondly, used it in the formulas here. And that is it. I hope it helps.